Green's theorem. The goal is to use Green's theorem to evaluate line integrals. Recall a curve C in a plane is positively oriented if it is traveled in a counterclockwise direction. Think in terms of angles. Remember, angles are considered positive if you trace them out counterclockwise, right? So same thing, if you trace out a curve in a counterclockwise fashion, usually we're talking about a closed curve when we say clockwise or counterclockwise. So picture a closed curve, C, and then oriented like so in a counterclockwise fashion, right? So theorem 1, Green's theorem. Let C be a positively oriented curve, piecewise smooth curve that is, and it's simple. What do I mean by that? It doesn't cross itself, so it doesn't look like a figure 8. That curve crosses itself, right? Whereas this curve, it might wiggle around, but this curve does not cross itself, except maybe it intersects itself only at what you might consider the endpoint. So C is a positively oriented, piecewise, simple, smooth curve that bounds a region in the xy plane. So this would be our C. It's oriented like this, and it surrounds our region R. The kinds of regions that we integrated over with double integrals back in the last chapter. Then as long as P and Q have continuous partial derivatives in the open region containing R, remember this is generic symbolism for the line integral over C with respect to the vector field F. This would be, if we're in the plane, this would be differential form for the same thing, different notation for the same thing, right? We're saying that this, in this situation, this line integral is equal to a double integral over that region R of dq dx minus dp dy dA. So we're relating a line integral to a double integral, okay? And in some situations, it will be much easier to evaluate the double integral than it will be to evaluate the line integral, and I suppose vice versa. Well, I'm just going to tell you about the idea of the proof. If you're interested, the full proof for a vertically simple and horizontally simple region is the full version of the proof is shown in the book. But basically, all you do is show that the integral over C of P dx is equal to the opposite of the double integral over R of this portion of it, dP dy, the derivative of P with respect to y. And then, so you prove it one piece at a time, and then you show that the integral over C of Q dy is equal to the double integral dQ dx. And you add, and then you just sum to get the result. So in this example, we have the integral over C. This is differential form of a line integral with respect to a vector field. Integral over C, x squared minus y squared dx plus 2xy dy. So the thing that we call P is going to be the guy attached to the dx. The thing that we call Q is going to be the guy attached to the dy. Okay? And C, does C satisfy the hypotheses of Green's theorem? It graphs to be, do you remember what a cardioid is? Yeah, it's a cardioid. Graphs to be a cardioid. So a cardioid is going to be a closed curve, first of all, and it is going to be a simple closed curve. Okay, so it's not going to intersect itself. You can graph this in polar mode on your calculator. But I think if you really wanted to, you could do it by hand. Plug in maybe 0 for theta. I'm just going to plug in the corners. Pi over 2, pi, maybe 3 pi over 2, and 2 pi. Okay, what do we get if we plug in theta equals 0? Cosine of 0 is 1, so plus 1 is 2, sure. If you plug in pi over 2, you get 0 for cosine of pi over 2 plus 1, which is 1. If you plug in pi, 0, because cosine of pi is negative 1, plus 1 is 0. 3 pi over 2, back to 1, 2 pi. Back to, what are we back to? 2, yeah. Same as if we plugged in 0, right? So if we think radially and angularly, that's hard to say, look in the 0 radians direction and go out 2. So 1, 2. And then plot your point. Pi over 2, you're out at 1, aren't you? So plot your point there. At 0, at pi rather, you're at 0, so here. And then, I don't know if you remember this or not, but when it's cosine here, the graph is symmetric to the x-axis. So if you know what the top half looks like, you know what the bottom half looks like. Now, how do I know it's a cardioid, first of all? Well, when the absolute value of this guy, we usually call this guy A, divided by this guy, we usually call this guy B. When that absolute value equals 1, it's a cardioid. And so I'm fairly confident that it's going to look something like this. That the cusp is going to come in like here, and then the bottom half will look like the mirror image of the top half. And if you want to, you could verify that on the calculator. That's not the best picture in the world, but that's fine. I don't even really need a picture to do this problem. I'm just going to use it for an illustration of my limits of integration. Well, 2 of my limits of integration. All right. So what Green's theorem says is this line integral should be equal to a double integral, because that curve C satisfies the hypotheses. And by the way, P and Q do too. The derivatives will be continuous. That won't be an issue here. And I don't think it ever will be in this class. So let's find the integrand of that double integral that this should equal. If you go back up and look, that double integral, the integrand is dq dx minus dp dy. So we're gonna find this, and then we'll just set up the integral over that region inside that curve. So, okay, let me just write out what we're finding. dq dx, the derivative of q with respect to x, it's a partial derivative, so use the funky d notation, minus the partial of p with respect to y. Okay, so, what is the partial of q with respect to x? 2y. Minus, what is the partial of p with respect to y? Negative 2y. Like that, right? What do we end up with for our integrand? 4y. Okay? So now, the integral then, generically, would be represented as the integral over r. This is r inside the cardioid, right? So generically, we would say it's the integral over r of 4y dA. Are we going to bother setting up in Cartesian coordinates here? That would be silly, right? No, but we're just trying to evaluate this thing. So let's go right to polar coordinates. What extra factor do you have to remember in your integrand? R, as the pirate would say, right? And then can I just pull the 4 out in front? And then what's y in polar? R sine theta. And then what you can do in your picture, so the reason I drew this picture is to remind you how to set it up in polar coordinates. Draw a representative spoke, right? Or a sector if you like. I just make a straight line segment, a radial line segment, that is, from the origin to the curve. And the endpoints of that radial line segment give me my inner limits of integration, right? So what's the point, the r value, the point closest to the origin? We're looking for r values here. 0. And then what's this r value at the end given by? The function itself, its variable. So 1 plus cosine theta, the function that generates the curve itself. And then, well, what does theta have to run from for the outer limits of integration to trace out that entire cardioid? 0 to 2 pi. Okay, so let's clean this up a little bit. It's 4 times the integral 0 to 2 pi of, I'm going to put the r squared in front. Well, actually, I'll put it in back. So sine theta r squared dr d theta. Does everybody see? Oh, and I'm missing the integral. There we go. That looks better. Okay. So all I did was multiply r times r, get r squared. Okay, now integrate with respect to r. What does that give you? Okay, r cubed over, for this guy, r cubed over 3, right? Now here's what I'm going to do. I'm going to pull out that denominator 3 out front, make it 4/3 out front. Make your life easy. Pull out those constants. The outer integral stays 0 to 2 pi. The sine of theta is not going anywhere. And then we just get r cubed evaluated from the inner limits of integration 0 to 1 plus cosine theta. And we still have the d theta on the outside. So we do that. We evaluate it. We get 4/3 integral 0 to 2 pi sine theta times what?
1 plus cosine theta cubed.
Well, okay, so 1 plus cosine theta cubed. And then minus 0 cubed, right, which doesn't do much. D theta? Everybody with me? Now, I don't know about you guys. I do not want to multiply out 1 plus cosine theta cubed. So maybe we could figure out a way to use u substitution here. So, yeah, let's let u equal 1 plus cosine theta. But don't actually make the substitution unless you really like doing that. Because then what's your perfect du? Negative sine theta, right? The derivative of cosine theta d theta, right? So what do we need to put in front of the sine theta then? Just the negative, right? And then compensate by putting a negative on the outside. So this, I mean, if you think about it then, this is really just, if you did make the substitution, this is really just u cubed du inside or after the integral symbol, right? Okay, so if you integrate, let me bring it up here, and just so I can keep everything on the same screen, let me shrink this guy down. Okay. So what do we get then when we integrate just u cubed? So we have negative 4/3 on the outside. Let's keep that there. And then you said 1/4, right? So I'll put that 1/4 outside as well, outside the brackets. And then that gives us our u to the 4th, right? Evaluated from what to what? 0 to 2 pi? So out in front, what do we have? Negative 1/3. Okay, if we plug in 2 pi, what's the cosine of 2 pi? 1, so we get 2 to the 4th. If we plug in 0. Oh, so we did all this work, and what did we get for an answer? Trolled. Now, we got 0, but that's okay. That's an answer. If this represented some sort of work done, then we're saying 0 work is done by the vector field, right? Now, here's an interesting problem. We're going to evaluate the integral over c y minus x dx plus 2x minus y dy, where c is the boundary of, so what is the region? The region is going to be this rectangle missing with the hole is the square here, the little square. So the region is the part with the green diagonal lines through it. Does that make sense? And what that means is C is not a simple closed curve like I showed you a picture of at the beginning. It has a hole in it. Well, let me put it this way. The region that C encloses has a hole in it. That square in the middle is not part of R, the region that C encloses. So, okay, first off, realize C is actually the union of two disjoint curves. One of the curves is the boundary of the big rectangle on the outside. See it? The other curve, it's the boundary of the square inside. And it looks like it's parameterized so that it's a clockwise parameterization. So it looks like a negative parameterization, but I'm going to convince you in a minute that it's not really a negative parameterization because you have to change your thinking a little bit. So how the heck do we do this if C is not one single curve, right? I mean, yeah, we can, it's not even connected, right? It's supposed to be a curve that's not only connected, but smooth, or at least piecewise smooth. But it's not, is it? But there is a way to make it piecewise smooth. And that's by adding in 2 more curves. So let me show you what I mean here. And this gets a little weird, but so is the rest of the class, so that's okay. So what we can do is on the x-axis itself, now I'm going to draw this off the x-axis so you can see what's happening, but I could put in another curve, C3, let's call it, starting at, it looks like, what is this, 1, 2, 3, 4, 5, 0. This point right here is 5, 0. Starting at 5, 0, I could put in another curve. Now, I'm not going to draw it on the x-axis because you won't be able to see both of them if I do that. But picture this on the x-axis, not where I'm drawing it. This curve in pink right here, I'm going to call C3. And then the same curve, the same line segment really, except parameterized in the opposite direction, I'm going to call C4. So C4 is also going to coincide with the x-axis. I'm going to draw it off the x-axis just so you can see what I'm doing. C4 is this guy right here. So C4 starts at this point is 1, 0. C4 starts at 1, 0 and ends at 5, 0. C3 starts at 5, 0 and ends at 1, 0. That's the only difference. The direction of the parameterization is different. Now, if you can draw the curve C and not lift your pencil, then it is at least piecewise smooth. Okay? So what is C going to become then? C is going to become, let me use a different color. C is going to become C1 union C2 union C3 union C4. And I'll show you why it's okay to change it in a second. But first of all, let's agree that then I've created a piecewise smooth closed curve. So one place we could start, say, we could have a starting point anywhere around this curve. Let's say I start here. Now, if I travel along this curve in a positive direction, because remember, that's a requirement for Green's theorem, the real requirement, or another way to think of the positive direction, is to always have the region that the curve encloses on your left. For simple curves, that's always true, right? If you have a simple closed curve, and this is your region, and you travel along it in a positive direction, then the region R is always on your left, isn't it? That's what has to be true. Say I start anywhere here, and I travel along the curve according to the orientation of the parameterization, according to where the arrows point. And I want to go all the way around the curve without lifting my pen. Then look, I go up to C3 actually, so I probably should have started, probably should have labeled them differently, but that's okay. And then look, so that whole way the area was on my left, right? The region was on my left. Now look, when I travel this way, although I'm going clockwise, the region is on my left, isn't it? And then I return to the x-axis, and I'm really traveling on the x-axis here over C4. And then I keep going around. And I've traversed the entire curves C, which is the union of C1, C2, C3, and C4, without lifting my pen. So this is at least piecewise smooth closed curve, and it's positively oriented. Even though it has a hole in it, we're going to be able to apply Green's theorem here. You might say integrating over the new version of C is not the same thing as the original version of C. But it is, because if you integrate over C, I'm kind of disregarding most of the notation here, then that's integrating over C1 union C2 union C3 union C4, right? But when these curves are disjoint, and we don't count the overlap here because they are oriented differently, and we are calling them different curves. When these curves are disjoint, integrating over this union of curves is the same as integrating over the sum involving or over each curve individually. But remember, C4 is just the opposite of C3. It has the opposite orientation. And so you can write it as, okay, you can write C3, well, let's leave C3 as is, and you can write C4 as negative C3. But you guys know that integrating over negative C3 is the same as the opposite of the integral over C3. And so these two integrals knock each other out, and you really are just calculating the integral over C1 union C2, or it'll have the same value of it anyway. So long story short, this is going to work. Green's theorem is going to work here by this special trick that we're using. Okay, so what does Green's theorem say? Remember what it says, the integral f dot dr, that's the integral, that's another way to write the integral over the vector field, or with respect to the vector field. It says it's the double integral over r of the derivative of, remember what it says, q with respect to x minus the derivative of p with respect to y dA. So what we're saying is we can calculate that given line integral by computing this. So let's go back and find dq dx. Okay, dq, okay, remember what's what here? This is actually p, right? P is y minus x, and q is 2x minus y. So what's dq dx? What's the derivative of q with respect to x? 2, okay. And fill in whatever we said. I think it was 2 for dq dx. And then what was the derivative of p with respect to y? 1, right? Just 1. So we get 2 minus 1 for dq dx minus dp dy for the integrand, which is just the double integral over r dA. And when the value of the integrand is 1, what is this equal to? What is this double integral equal to? The area of the region, R. Oh, but the region was formed using rectangles. We know how to find the area of rectangles really well, don't we? Okay, so it's actually a rectangle with a hole in it, right? So if you look at the big rectangle here, it goes from negative 5 on the x-axis to 5. And it goes from negative 1, 2, 3, negative 3 on the y-axis to 1, 2, 3. So what are the dimensions of this rectangle? The big rectangle, that is. 10 by 6. So the area of the big rectangle is 10 times 6. But we've got to subtract out the whole. The whole is a square that goes from negative 1 to 1 on both axes. So it's actually a 2 by 2 rectangle. So 10 times 6 minus 2 times 2, 56 square units. Would you buy that? I'm just going to put 56 because we may not be referring to area when it comes to the line integral. But one thing I want to point out is if we had evaluated this line integral here by summing the two individual line integrals, 1 over C1, 1 over C2, we would have been using a line integral to find area, wouldn't we? So, I mean, that was kind of an accident of this problem, but it gives us a result that line integrals for certain P and Q can be used to find area. And that's the corollary of Green's theorem. So theorem 2, I'm calling it, corollary to Green's theorem. If R is a plane region bounded by a piecewise smooth, simple closed curve, same requirements for Green's theorem, oriented counterclockwise, then the area of R is given by 1/2 integral c x dy minus y dx. Do you think this would be hard to prove? All you got to prove is that dq dx minus dp dy, the integrand on the double integral from Green's theorem, is equal to 1, like we had in the last example. So which one of these, x or y, is, and be careful, take a close look, which one is p? The y, because it's attached, it's in the different order than you're used to, but it's attached to the dx, right? And so q must be x, right? So what is dq dx? That's just 1. What's dp well, okay, you've got to include the negative with the y, right? So technically p is negative y. So what's dp dy? Negative 1. So if you do the subtraction, you actually get 2, and that's what the 1/2 is for, right? So then, okay, yeah, it really is 1. The dq dx minus dp dy times the 1/2, it really is 1. And so, yeah, this line integral must represent area. But there's an infinite number of ways you could create area formulas. So here's 2 others. If you just took the integral over c of x dy, and you leave off the 1/2 and you leave off this part, then, that x is still q, right, from the vector field? So dq dx would be 1, and dp dy would be 0. So you'd still have an integrand of 1. So this would be yet another formula for a line integral that represents the area of the related region R. Alternatively, another one you could come up with is delete the 1/2 and delete this part. And you could say, how about negative integral over c of y dx? Then p is equal to y once again. And when we write it this way, that means q is equal to 0. And if you take dq dx minus dp dy, because of this negative here, you will get 1 for your integrand that way as well. So any one of these formulas and a million others could be used to find the area of a region. So let's do that. Let's use a line integral to find the area enclosed by a circle of radius a. So this will be the weirdest way you ever find the area of a circle, the formula for the area of a circle. All right, but this will be good practice as well, because we need to, if we're going to use a line integral to find the area of a circle of radius a, we're going to need to parameterize the boundary of that disk, the boundary of that circle, right? What would the parametric equations be? So circle radius a, it's a, let's use t for our parameter. So a, let's use, actually, to keep it positively oriented, let's use for x a cosine t. And for y, let's use a sine t. What does t run from? 0 to 2 pi. How do I know this works? Well, what's the equation of a circle of radius a? X squared plus y squared equals a squared. If I plug in a cosine t for x and a sine t for y, I'll get a true statement, because if I factor out, you end up squaring it. If you factor out the a squared, inside the parentheses, you'll have cosine squared t plus sine squared t, which equals 1. And so you'll end up with a squared equals a squared if you plug those in. So, you know, you do this often enough, you'll just memorize, oh, okay, yeah, I just take the radius times cosine for x, for the parametric equation for x, and then I take the radius times sine for the parametric equation for y. And if you got to make sure it's x equals a cosine, because if you switch those around, it won't be positively oriented. The curve would be traversed. If you make x equals a sine t and y equals a cosine t, the curve would be traversed clockwise. And so you'd get the opposite answer of what you wanted. Okay. So that's nice, right? So which one of these formulas do you want to use? I'm thinking this one's kind of nice because it doesn't have two terms in it. It doesn't have a negative, right? So integral over c x dy is the area formula I want to use here. Integral over c x dy. Okay, so this is differential form. I like differential form, you guys, because all you have to remember when it's in differential form is write everything in terms of t, right? That's all you got to remember. So, let's do the limits of integration. Well, to trace out that circle, what does t have to run from? 0 to 2 pi. So integral 0 to 2 pi. What's x in terms of t? A cosine t. Can you get dy in terms of t? What do you do with this guy? Let me make a little more space. What do you do with this equation? Just take the differential, right? So what does dy equal? A cosine t. Beautiful. dt, right? And then, so that's what I'm going to plug in right there. A cosine t dt. And then, of course, everything is squared. So can I pull an a squared on the, a is a constant, right? Let me pull that outside. So a times a squared, let me pull that outside, the integral. So a squared integral 0 to 2 pi. What's on the inside? Cosine squared t dt. Okay, so guys, channel your Calc 2 class. How do you integrate? What do you do with the cosine squared when you're trig identity? Yay, trig identity. So okay, so cosine squared. Whoops. I was recopying it, but what we're saying is cosine squared t is equal to 1 plus cosine 2t all over 2, right? Or 1/2 times the whole thing. And I'm going to rewrite it like this. A squared over 2, because you know how much I love to bring the constants to the outside. And then on the inside, so a squared over 2 integral 0 to 2 pi 1 plus cosine of 2t dt. Everybody with me? Okay, let's integrate. Leave the a squared over 2 on the outside. Integrate 1 with respect to t. What do you get? T. Integrate cosine of 2t with respect to t. What do you get? So technically it's 1/2 sine, right? Although you might end up with the right answer if you made that mistake. So 1/2 sine of 2t, integral 0 to 2 pi. Okay, plug in the upper limit for t, and you get 2 pi. Plug it in for, okay, you end up taking the sine of 4 pi, right? Which is what? 0. And then what happens when you plug in the lower limit on both of them? Everything zeroes out. So you just end up with 2 pi, but that's good news, because then you get the right formula, right? You get a squared times pi, or pi times a squared. That's pi times r squared, right? Pi times the radius squared. So that's the weirdest way you're ever going to find the formula for the area of a circle. So theorem 3, let's suppose f is the vector field PQR again, and has continuous first partial derivatives. That just ensures that the component functions are differentiable, which ensures that you have very well-behaved component functions. In an open connected region R, and let C be a piecewise smooth curve in R. The following are equivalent. F is conservative. Okay, first of all, let's review. What does it mean to say F is conservative? Yeah, it's a gradient. So in other words, there exists a scalar function f, little f, such that you take del little f, the gradient of little f, you get f, big F, the vector field, right? That's not true with all vector fields. So if that happens to be the case, if f equals del f for some little f, then f is conservative. And then if f is conservative, that's true, or that implies that the integral is independent of path. So going from a to b, that's just fundamental theorem of line integrals. You already know that. But we're also saying you can go from b to a, and that's harder to prove. We won't try to prove that today. So saying that they're equivalent means you can go from a to b or b to a. So in other words, if the integral is independent of path, then f is conservative. But there's another result that doesn't seem to relate that's equivalent to the other two. If you can say that the line integral is equal to 0, now it's got to be true for every closed curve C in R, then the vector field F is conservative and it's independent of path. So C is equivalent to both A and B. So the note says, so we're assuming that the integrand from Green's theorem is 0. So if it's equal to 0, then for every simple closed curve C enclosing R, would you agree with this statement? That the line integral, so this is just one notation for the line integral. This is just to remind you that this is differential form for the line integral, two equivalent ways of representing line integrals. For Green's theorem, it's equivalent to saying that the double integral with integrand dq dx minus dp dy dA, so that's equal to the line integrals for closed curves. And if we know the integrand is equal to 0, then certainly the value of the integral is equal to 0. The double integral, that is. Does that make sense? Okay. So what does that mean? If it's true, if this is always true that dq dx minus dp dy is equal to 0, then what does that have to mean about f according to the last theorem? That's it. It's conservative. You win the prize. I don't know what the prize is, but. So this gives us a test that I actually mentioned in the last section. Remember, if dq dx equals dp dy, okay, so think in this guy, just add dp dy to both sides. And you have an equivalent statement. So if dq dx equals dp dy, then f is conservative. And so that I didn't actually prove that in the last section, but I mentioned that result. So Green's theorem helps us prove that result. So f is conservative.